Okay, thank you very much. Well, it's a pleasure to be back in Boulder. So I think I did this once 11 years ago, and I had fun then. So I expect I'll have fun now. So so I was asked to talk about topological insulators, and so I thought I would broaden that a little bit to topological band theory in general. So let me just give you a little bit of an outline of where I'm going to go over the course of the 4 lectures. So I'm going to start off with some sort of general things about topology and band theory. So topological band theory. And then that'll segue into a discussion of the time reversal invariant topological insulators, so the Z2 in 2, 3 dimensions, plus some generalizations. And then I'm going to give a discussion of topological superconductivity, which one can sort of understand in a similar language. And I think maybe that'll be something that you're going to see over again. But I think it's nice to sort of see how the language of topological band theory that I'll be developing sort of describes these things in a unified way. So, okay, and plus generalizations. Okay, so this is the plan, I think what I'll do is start by so one thing I'll say is that one thing that's really been new over the last decade has been the appreciation of the interplay between topology, which we heard a little bit about this morning, and also symmetry. Okay, and so symmetry, of course, is one of the most familiar things that we learn about in physics. If you have a circle, you can do things to it. You can rotate it or you can reflect it, and it kind of looks the same, right? And so understanding what you can do to a system that keeps it the same is a very powerful conceptual tool that allows you to simplify problems. It allows you to understand conservation laws. And also, as we discussed this morning, it's a classification tool for classifying phases of matter. Okay. In particular, if you can just understand what symmetries a phase of matter breaks. So, for instance, if this is the order parameter of a magnet, then it breaks some rotational symmetry. Then that's a classification tool for classifying phases of matter. Okay. And there are many kinds of symmetries. There are crystalline symmetries, translation symmetries, discrete translation symmetries, rotational symmetries. There's gauge symmetry. There's many kinds of symmetries that are very powerful to think about. An equally powerful tool, though, is topology. So what topology is about, of course, is what is it that stays the same when you deform something? Okay, and so the classic example of that is if you look, what's the difference between a sphere and a donut? Okay, so a sphere has a genus 0. Whereas a donut has a torus has a genus 1, which is basically counting the number of holes. And so what topology is about is it's how do you tell the difference between these kinds of things. And so you can smoothly deform a sphere into a pancake, and nothing drastic happens along the way, but you can't change it into a donut without poking a hole in it. Okay, and so how do you describe this? So let me just give you a a very simple example of how you might think about this. How could you, let's suppose you were living on the surface of this donut. How could you tell it was actually a donut and not a sphere? And so there's a very famous and beautiful theorem called the Gauss-Bonnet theorem, which says that if you have some surface and you integrate over the surface the Gaussian curvature, and so what the Gaussian curvature is it's basically you have radii of curvature in two perpendicular directions, so it's the product of the radii of curvature. That's what the Gaussian curvature is. If you integrate that over the surface, then you're guaranteed that you get a quantized answer that's quantized in units of 4 pi, and the integer multiple of 4 pi tells you what the genus is. Okay, and so this is actually, for a sphere, this is easy. You can do this in your head, right? Because the Gaussian curvature is just 1 over the radius of the sphere squared, which when you integrate over the sphere just gives you 4 pi. Okay, and for the torus, maybe it's not too hard to see that the torus, you can basically think of it as being flat. So its Gaussian curvature is 0. So you get 0. Okay, so you can sort of understand those two cases. And so so this is an example of a topological invariant. Okay, and so one of the things that we're going to develop is how we can develop similar kinds of mathematical descriptions to describe quantum states of matter. Okay, so for topological phases of matter, so what one needs, so in topology, what one's concerned with is sort of, what things stay the same under smooth deformations. Okay, and so we need some notion of a smooth deformation for describing states of matter. And so the idea that I want to suggest is that I can think of topological equivalence as arising from adiabatic continuity. So, and so what this requires, so the adiabatic principle in quantum mechanics tells you that if you have a quantum state that is separated from all other quantum states by a finite energy, then that energy difference defines a time scale over which you can smoothly change your Hamiltonian very slowly, so that you're guaranteed to stay in the same state the whole time. You don't induce any transitions if you go slow enough. Okay, and so this is the adiabatic principle, and so you can use this adiabatic principle if you have an energy gap. So if you imagine now I have some deformation, and I have quantum states where so I have a ground state and excited states. Okay, if I have an energy gap, then I can slowly deform this slow enough so I'm guaranteed to stay in the same state. And so in that sense, I'm staying in the same phase. Okay, and so this idea of a phase of matter is really something that is topologically equivalent. Okay, and so that's what we want to say. And so now, of course, the question that this immediately poses, if we have this notion of topological equivalence for phases of matter, the question is are there any non-trivial phases? Okay, and so what would have to happen in that case is, in order to get to a non-trivial phase, one would have to go through some quantum critical point where where the energy gap goes to 0. Okay, and so okay, and so what we want to do, so our goal here is we would like to be able to classify and characterize, the different kinds of phases that you can have. Okay, and I want to add to that with or without symmetries. Okay, and so one can refine this notion of a adiabatic deformation to be one which preserves certain symmetries. Okay, and so that's going to play a key role, for instance, when we talk about the Z2 topological insulators. Yes, question? It could be, yeah, absolutely, sure, absolutely, yeah. No, yeah. So my only point is that to get from one state to one that is topologically distinct, you can't go. You have to go through something, through some critical point. Okay. Okay. All right. Okay. Now, so we'd like to be able to classify all phases of matter with with or without symmetries, but of course, that is a incredibly hard problem. Okay, one which I don't think we still have a complete solution of. Okay, and because to classify phases of matter, one's really confronted with the many-body problem. Okay, and the many-body problem is hard. Okay, it's also interesting. So there are many interesting things that one can learn, and some of the things that we learned about this morning are examples of interesting many-body problems. But the approach that I want to take is I want to try to simplify things into a more manageable set of problems. And so rather than think about the general problem of trying to classify all possible electronic or quantum phases of matter, what I want to do is I want to classify and characterize what I will call single particle topological phases. Okay, so these are, say, topological electronic phases that can be described using non-interacting fermions. Okay, now, of course, that doesn't mean that the only problem I'm interested in is the non-interacting fermion problem. Okay, the problem I'm interested in is problems in which the sort of mean field theory of the interactions, Hartree-Fock theory, gets it right. Okay, and so there's a wide class of interacting quantum systems whose ground states are adiabatically connected to the ground state of non-interacting fermions. Okay, and so those are the ground states that it's a manageable goal to try to characterize. Okay, and so that's what I want to do. And so I want to emphasize that this theory doesn't become wrong when you have interactions, so it's just that we're describing phases which have interactions, but the interactions are not so big that you've gone into some other phase. Okay. Okay, and now. So one further simplification that I'm going to take advantage of is symmetry. okay, and in particular translation symmetry. Okay, now this is not an essential thing. So one can there's much to be said about even the single particle topological phases. You know, when you allow disorder and you allow translation symmetry to be violated. But things are particularly simple if we believe in translation symmetry, so that we're talking about crystalline matter. Okay, and so this then is the subject of the band theory of solids, and so this is what leads to what I call topological band theory. Okay, and so I just want to pause here. Band theory. Of course, everybody learns about band theory, and from the sort of first solid state physics course that you take, and it seems kind of a little bit old school, right? And I just want to it's useful to sort of step back and sort of appreciate how consequential a theory that is. Okay, so band theory, when it works, it doesn't always work, but when it works, band theory works really well. Okay, and it allows for a quite detailed understanding of actual real materials. Okay, and it's that understanding of real materials, of course, that's responsible for the fact that you have a powerful computer in your pocket. Okay, so band theory is a consequential theory, and so we want to understand the consequences of topology in that context. Okay, so let me sort of start by just reminding you about band theory. Okay, and I'll do this quickly. So first of all, in band theory, again, we've by taking away the interactions, we allow ourselves to solve the many-body problem by solving many single particle quantum mechanics problems. Okay, and so we solve a single particle Schrodinger equation. We have some single particle Hamiltonian, which commutes with translations. So T of R is a translation by a lattice vector R. Okay, and if this is the case, then you know that you can choose your eigenstates to be eigenstates of the translation. So that means that I can write my states. I can label my states with a momentum. Like that. Okay, or alternatively, what I can do is I can define block states which are periodic in the unit cell. So what I can define is I can define this state psi k as e to the I k dot r, where this r now is the position operator, okay, times a block state, where this block state is periodic. And so the point is that this state, all of the information in this state is contained within a single unit cell of the crystal. And so this you can solve by solving a much smaller problem than this. Okay, and so this is one of the power, taking advantage of the power of translation symmetry. And so this U then will be an eigenstate of the block Hamiltonian, which is basically do I have my, I want to have plus and minus. Okay, so the point is that by doing this block, decomposition, one ends up with a single particle problem, which is now parameterized by the momentum. Okay, and K, of course, is in the Brillouin zone, which is a is defined periodically. It's a torus in d dimensions. So in one dimension, the Brillouin zone is a circle. In two dimensions, it's a torus. Okay, so this then leads to a band structure. And I can think of the band structure as basically being h of k. And h of k has a set of eigenvectors and eigenvalues. And so if I plot the so I'm going to have a set of eigenvalues and eigenvectors. And so if there's a gap separating the valence band and the conduction band, then one has this gap separating the ground state from the excited states. Okay, and so what we know, so this goal of classifying topological band structures then becomes the goal of classifying band structures that have a gap that separates the conduction band and the valence band. Okay. Okay. Now, so there's something important here, which is by going to this block formulation, we ended up now where we're classifying a Hamiltonian which is now parameterized by a set of parameters. Okay? And whenever you have a Hamiltonian that is parameterized by a set of parameters, then that invites one to think about a very powerful conceptual tool, which is the Berry phase. Okay, and so let me introduce the Berry phase. You see, the Berry phase arises whenever you have a system that has a parameter. Okay, and the reason it arises is because the wave function in quantum mechanics has an intrinsic ambiguity to it. Okay, the phase of the wave function is ambiguous, and what that means is that if I have an eigenvector u of k, then an equally good eigenvector is one in which the phase is modified by, in which the phase is changed. And this change in the phase could very well be dependent on the parameter. Okay, and so this transformation having this parameter dependent change of the phase reminds you of an electromagnetic gauge transformation. Okay, it's the same sort of story, and when you have the vector potential and you do a gauge transformation, you change the vector potential. Okay, it's the same here. The only difference is that instead of having living in real space, this gauge transformation is changing in momentum space, or whatever the space of parameters that you have. Yes. Oh, I mean, yeah. Sorry. Yeah. Thank you. Thanks, Nick. So, Yeah. So and so what this invites us to do is to define the analog of the vector potential. Okay. And so that's the Berry connection. Which I'll call A, the same letter as we call the vector potential. Okay, and so it's pretty easy to see that if I do this change in the phase, then the Berry connection transforms in exactly the same kind of way as the electromagnetic vector potential. So in particular, under this gauge transformation, so UK, the derivative with respect to K is going to pick up a term here, which gives us A, but then we're also going to pick up a gradient of phi K. And so A is going to go to A plus the gradient of this phase. Okay? And so of course A by itself is not gauge invariant. It depends on this arbitrary phase. But what is interesting, just like in electromagnetism, the vector potential by itself doesn't have an independent meaning, but the magnetic field, which is the curl of the vector potential, does. Okay, and so this invites us to define the Berry phase, which is the analog of the magnetic flux. So if I have any for any closed loop, let me call it C. Then so let's suppose I have, so this is C. Then what I can define is I can define the line integral of the Berry connection, and that is guaranteed to be gauge invariant. Okay, so this is over C. Okay, and I could equally well write that. I could use Stokes' theorem basically to write that integral of A around the boundary as an integral of the analog of the magnetic field where F is essentially the curl of A is the Berry curvature. I know. I'll get to that. Yeah. Nick is right. See, it is contractible.
How do you know that the spectrum of HK varies continuously?
If the Hamiltonian is short-ranged, okay, so that I think is an implicit assumption that I'm making that the Hamiltonian is a local operator that doesn't have long-range pieces. Then H of K is essentially the Fourier transform of H of R. So if it's short-range, it's not going to have singular behavior. Yeah. Yeah. But that's an important point, which is that the principle of locality is an essential is essential for thinking about these topological
so is it just like Fourier transform where you just need exponential fall off to have smooth?
Certainly, exponential is good enough, and when one could ask whether you could maybe have it be a little bit less than that. And I don't know the exact what the exact requirement for how short range has to be. Yeah, but certainly certainly exponential is good enough.
That gives you a nice Hamiltonian. That's not necessarily saying things about the spectrum. You asked about the spectrum being continuous.
Well, I want to say that h of k is continuous. Okay, and if h of k is continuous, then the spectrum I expect will be continuous as well. That's what is that what?
Well, there's various versions of it you can have.
Okay.
But you may not want to get it.
Probably not. Okay. Okay, so this is an important concept, and there's a very important example. Okay, and this is the most important example. So and it's nice and simple. It's the two-level system. Okay, so let's suppose that we just have two states. So our Hamiltonian then is going to be a 2x2 matrix, parameterized by K. Now, any 2x2 matrix, you can write in terms of the Pauli matrices. So I can write this. Well, let me write it like this. Okay. Alternatively, I could write this as d0 plus dz dx minus I dy. Okay.
You're talking about lattices, not really two-level system, more like a lattice.
Yeah, so I'm talking about a block Hamiltonian, which is you see, I mean, look, the concept of baryon phase is more general than band theory. It applies to any system where you have a quantum system which is parameterized by some set of parameters. And so I'm saying I have a two-level system which is parameterized by K. Okay, and no, you're right that if as a band theory, it's a two-band model. Okay, so it's a model where maybe I just have two orbitals per unit cell. Okay, and so then that'll be described by a two-band Hamiltonian. But the baryon phase, in a sense, it's more general than that. Okay, it can describe a spin, for example. Okay, and yeah.
So in principle, there should be a lot of generalization of the topological insulators to those non-band systems.
Sure. I mean, but I'm not sure what you mean by insulator. But
There's a gap.
well, right. But yeah. So yeah. Okay. So, I mean, this is like the Hamiltonian of a spin in a magnetic field. So this piece is just a constant piece. It doesn't change it just changes the overall, zero in energy. But this is like a magnetic field that couples to the spin, which, and so what we know, so you can just read off what the eigenstates of this. There's going to be two, and you know that they're going to be. I'm sorry. I should put D0 in there. Okay, and so if we pick one of the eigenstates, then the eigenvector only depends on the direction. Okay, and so one can ask the question now: if we take K through some closed loop, we can ask what the Berry phase is. Okay, and what we know is that since the state only depends on the direction that this D vector points in, it only depends on the direction of the magnetic field, then the Berry phase is only going to depend on the trajectory that the direction of D sweeps out on the unit sphere. Okay, and in fact, the answer is very simple. So let's imagine that we have, so here's the unit sphere where I have, where this is D. So if D of K sweeps out, a loop, sweeps out a curve on the unit sphere, then the famous result is that the Berry phase is equal to 1/2 of the solid angle swept out by D. Okay, and so this is an important result. If you haven't been through this, then this is a good exercise to make sure you know how to do. Okay, this is basic. This is a basic thing. And so an example of this is what I always like to refer to as my favorite minus sign. So if you have if you have a spin and you rotate it by 2 pi, so you just rotate it by 2 pi, then the angle on the sphere, the solid angle on the sphere that you sweep out is half of the sphere, which is 2 pi. And so the Berry phase that you get is pi. And so that's the minus sign that a spin picks up when you rotate by 2 pi, which we already talked about a little bit this morning. Okay? Okay.
You told us the significance of Berry phase. You said how to calculate it, but you didn't tell us what it means.
Not yet.
So even to conclude that there is some...
I will.
science
I haven't gotten there yet. I haven't gotten there yet. Yeah. So it's a very fair question to ask. What does this have to do with band theory? So what I hope I've convinced you is that one can define a Berry phase in band theory. So the interesting question is what does it mean? Okay, and I will answer that. And in order to answer that, I want to answer it in the simplest context, which is one dimension. Pardon me?
How long ago was this idea?
Which idea?
Define the connection.
Berry, well, so actually, other people in the room probably know the history. I mean, so Berry, it goes back well before Berry, I believe. And I don't know how far back it goes. Do you know, Nick? I don't know. Yeah.
Berry is 1980.
Yeah. I mean, in the context, so for what I'm about to tell you, applying this Berry phase to band theory, that was more, I think, in the 1990s, I believe, late 80s, 1990s. Oh, no, absolutely. No, forget it. Yeah, that was 80s. Nick, you're absolutely right. Yeah, I don't know why I said that. Yeah, absolutely. Thales. In fact, I will. Yeah. Okay. Okay, and so what I want to describe, so the punchline that I'm going to get to you is that the meaning of the Berry phase is it is an electric polarization. Okay, and so I want to tell you about the electric polarization in one dimension.
You also didn't mention Berry's actual adiabatic theory. But adiabatically transporting something, apart from the dynamical phase, you pick up the Berry phase. You just defined the Berry phase. But
That's true.
maybe that's what Victor was getting.
Yeah.
The actual statement from Berry is connected with
Well,
adiabatic.
I agree with that, but that's not what I'm going to be using. Okay. Yeah.
Carry on.
Yeah.
I'll mention it tomorrow.
Good. Okay. Okay. So
But Charlie, this electric polarization has nothing to do with this.
it will.
Sense of
It will.
what does it.
It will. Yeah. You'll see. Yeah. Yeah. So okay. So let me just remind you. Let's go back to sophomore E&M and remember what polarization is. So if you have electric dipoles, right? Then if you have a density of electric dipoles, then you have a polarization. So classically, P is equal to the dipole moment in one dimension per unit length. Okay, and so the thing if you have a bunch of if you have a density of dipoles, then if the polarization is constant, there aren't any charges. All the charges cancel each other out. But you can have bound charges. And so in the bulk, you can have a bound charge density, which is the divergence of P. And then at the end, there's going to be a leftover plus charge at the end and minus charge at the other end. So I can call this Q end. And Q end is just going to be equal to the polarization dotted into the normal of the end. Okay? And so lots of materials are polar, and they have these dipole moments. And so you can ask the question, in band theory, how do you actually compute what the polarization is? Okay? So how would you measure what would you do to measure it? Well, you just measure the charge at the end. That's how you could measure what the polarization is. But so the problem is that in band theory, what you do, in order to do, you always put it on periodic boundary conditions, right? So that you can define K, and so you don't have the end to be able to measure the end charge. Okay, and so you can ask the question, well, what is it? I have some band structure. What property of that band structure tells me what the electric polarization of that insulator is? Okay, and what I want to convince you of is that, in fact, it is a Berry phase. And so I'm going to give you a couple of arguments. Okay, and so what I want to argue to you is that the polarization is in fact the Berry phase evaluated around a loop, which is the entire Brillouin zone. So this Brillouin zone is, in one dimension, is a sphere. So it's going from so K is going from minus pi over A to pi over A, essentially, right? So it's going around the one-dimensional Brillouin zone where minus pi and pi are the same point. Okay, and of course, A is the usual primary connection. Okay. So I want to convince you that this is true. And so the way I'm going to do it, I'm going to first try to convince you that this quantity kind of smells like the electric polarization. Okay, and then I'll give you a slightly more rigorous argument. Oh, I see. Okay. Okay. And so the first argument that I want to give you that shows that these kind of look like the same thing is I want to show you that they both share the same intrinsic ambiguity. Okay, so let's think about the polarization in the bulk. This thing. So if I'm going to measure it by measuring the charge at the end. Now the thing about it, the charge at the end is not completely determined by the electronic structure of the bulk, because if I have my my one-dimensional insulator with a polarization, so maybe it has some charge at the end, but who's to keep me from just adding an electron at the end without changing anything in the bulk? That's just as good a end of this as well. Okay, and so for that reason, this polarization can only be defined modulo the electric charge. Okay, so Q, the end charge, is only equal to P mod E. Okay. Now, of course, so I can change the charge at the end by any integer number of electrons just by adding electrons. I can't change it by a fractional number of electrons because I don't have fractional electrons that I can add to it to the end. Okay, without changing the polarization. Okay, so the fractional part of the end charge is perfectly well defined, but the integer part of it is not. Okay. And so this is just this is a feature of the classical just of the polarization. So so now what I want to explain to you is that the Berry phase has exactly the same issue. Okay, and so let's think about the Berry phase, how the Berry phase changes under a gauge transformation. Pardon?
Isn't a perfect termination well defined? Supposed to have a bulk, terminate. Can terminate in a perfect way. I don't have to add.
But you could.
I could, but there's a well defined perfect.
Only if you're in the limit where you have atomic. So certainly if your insulator is built out of atoms that are really inert atoms that keep where it's well defined which electron is living on which atom, then I think I can do that. But you see, the problem is that in a band structure you don't each electron doesn't have its own atom that it lives on. Okay, and the ambiguity there then becomes the problem of you can't specify which atom each electron lives on, and so if you moved all the electrons over by one, you can't tell that you did that. And if you moved all the electrons over by one atom, okay, then you'd have an extra end charge at the end. Okay, and I think it's only if you really are in a limit where each atom is not, sharing electrons with the other atoms, where you're not, where you're really in the atomic limit. Okay, that you can really, that is really well defined. Now look, I mean, there's going to be a happiest end, that has the minimal charge at the end. That's certainly true. Okay. Pardon?
Lowest energy.
Lowest energy. Yeah, that's what I mean. Yeah. Okay. All right. So what I want to return to this question of how the Berry phase changes under a gauge transformation. So again, I want to imagine my I do some k-dependent gauge transformation, and so let's ask how the Berry phase, which is the integral over the Brillouin zone of A, changes. Okay, and so that's going to go to what we had before. Okay, but now, Nick, we have to be careful, right? Because in what I was doing before, I implicitly assumed that this phase had to be single valued. Okay, whereas when I'm going, so and that was a reasonable assumption if this parameter space that my loop is living in is contractible. Okay, because if it's not single valued, if the phase, for instance, winds by 2 pi, if the loop is contractible, then there'd have to be a singularity somewhere in the middle. And so we ruled that out. Okay? But the Brillouin zone is a little bit different because the Brillouin zone, up here, this loop is not the boundary of an interior. Okay? And so there's nothing wrong with having the phase wind by 2 pi when I go around, and that defines a perfectly smooth gauge transformation. Okay, and so now what we see is that under this large gauge transformation, in which the phase difference when I go around the Brillouin zone changes by 2 pi times an integer, then the Berry phase goes to the Berry phase plus 2 pi an integer, or equivalently, the polarization goes to the polarization plus E, given this definition of the polarization. Okay, so what we see is that this ambiguity of adding another electron onto the end is reflected in the ambiguity of the Berry phase on a non-simply connected loop due to a large gauge transformation. Okay. Yes. Oh, yeah, thank you. And this should be E times N. Yeah, thank you.
So I feel like I can measure absolute value of polarization. Maybe measure the absolute value.
Well, no, you can measure the absolute value of the charge at the end. That's what you can measure. Assuming that's what you're thinking of measuring.
See, so what's the difference? So can you explain to me just what the difference between that and the T?
I could think of if I change the polarization by 1 unit, by E, and I remove an electron from the end, that'll have the same end charge. So you would conclude that those are the same. Yeah. Okay. All right. Now, maybe a smarter way of measuring the polarization, though, would be to say, I'm going to start from a reference system where I know, say, the polarization is 0. And then what I'm going to do is I'm going to smoothly change my system and ask myself, and when the polarization is 0, maybe the end charge is 0. I can sort of zero my end charge. And then I can change my system and then measure what the end charge is after I did the change. Now that's provided I make sure that I didn't add any extra electrons at the end in that process, then that should be a well-defined thing. Okay? But what you're measuring is you're measuring the change in a polarization rather than the polarization by itself. And so that is something which is perfectly well-defined.
Are you saying charge at the end is not just polarization dot into an add? You can also add additional charges.
Yeah, why not? You can add, yeah.
I would have thought that is the charge different.
No, so here's the thing. So to what extent is the charge at the end determined by a property of the bulk? Okay? And my contention is that it's only the fractional part of the charge at the end is determined by the bulk, because I can always just add electrons to the end. Okay? And so now, if you want to define P to be Q end, you can do that, but then it's not a property of the bulk, because if I add an electron at the end, then you'd say you have to change P. So I'm trying to define something which I will call a polarization, which is a property of the bulk, okay? Which is something that conceivably maybe you could try to compute in a band theory, okay? Which is really, it's a property of the bulk, and there what I'm saying is only the fractional part of that that's well defined, okay? But changes in P are well defined. And so let me just explain that. Okay, so what I want to imagine now is that I introduce a new parameter in my system. So let's imagine that I have my state. I want to introduce a new parameter, u of k and lambda, and I can think that lambda maybe is like a function of time. It could be some knob that I'm turning. Okay, and so I can define the change in the polarization, which is P at lambda equals 1, say, minus P at lambda equals 0. Okay, and so let's think about what that would be. Well, so if I draw this picture now, so now I'm going to draw a picture of lambda and k goes between minus pi over a and pi over a. And lambda goes from 0 to 1. And so if I want to compute this change in the polarization, then what I do is I'd compute the Berry phase on this loop and then subtract the Berry phase on this loop. Okay? And so now of course you have to remember that this is that plus k and minus k are, plus pi and minus pi are the same. So this is really now like a cylinder, okay, with a top edge and a bottom edge. Okay, but now the loop on which I am evaluating the Berry phase is the boundary of an interior. It's the boundary of this. Okay, and so I can write this. So if I call this whole loop C, then I can write P delta P is equal to over this total loop, which is the combination of these two, and that I can write as an integral over the interior of this loop of the curl of A, basically. So I can use Stokes' theorem to evaluate that. So then this is completely gauge invariant. Okay, and so so I can use this this Berry phase formulation of the polarization, if you will, to compute this to compute the change in the polarization, and there everything is well defined. Yeah. Okay. So remind me, Joe, what's the time? 3:45. Okay, good. Okay.
But notice you're sort of assuming that you can close the two blue contours by adding the two imaginary yellow ones.
Oh, but the yellow one isn't imaginary, right? Because this line is the same as this line. It's a circle. No. The two yellow lines, they aren't lines. So this is really, if I could draw it like this, right? The yellow line is, the two yellow lines are just this at pi, right? So so there's nothing that, that's just an artifact that it's hard to draw it on the chalkboard, okay? But the important point, though, is that if I do a large gauge transformation on this one, I'm forced to also do it on this one. Okay? Because if I didn't, then there would have to be some singular point in the middle where there was so that would not be smooth. Okay? Yeah. So that's yeah. Continuous. Yeah. Yeah. Okay. All right. Okay. So all right. So now let me give you one more argument to support this proposition here. Okay, which is, what if you actually were going to try to, compute the polarization? What might you do? So if you had a a bunch of polar atoms, that weren't talking to each other, that just form a inert insulator, then what you do is you just say, well, I'm going to calculate the polarization by just evaluating the dipole moment on each atom, right? And that's a situation where I know which electron lives with each atom. So you might think that what you should really try to do is compute some sort of E times some expectation value of R. All right, that's what you'd like to do. Okay, because R expectation, this is like the dipole moment. Okay. The problem, of course, is that the states, the block states that you're evaluating they're extended across the entire system, and so this thing, and they're defined for periodic boundary conditions. So this doesn't make sense. Okay. So but it would make sense if you could evaluate it in a state that is localized. Okay, and so so this requires localized state. Okay, and so so what one can do is one can define a basis of states for my states in the energy band which are localized, and these are called Wannier states. Okay, and so the Wannier states are defined for any lattice vector R, and I can write. Let me. Okay, so so this R hat, this I just mean this is the position operator. So little r is an operator on the Hilbert space, whereas capital R is just a lattice vector. Okay, and so so it's essentially what you're doing here is, you know, I have my block states which are defined for every value of k. And they're defined smoothly. I can try to define them smoothly. And this is essentially taking the Fourier transform of that. Okay, and so provided UK is smooth, then when I Fourier transform, it'll be something which is reasonably short ranged. Okay, and so so this then. If I have my lattice vectors, so these are my lattice sites, and then, you know, so this Wannier state will be some, reasonably localized wave function. Okay. Now, the problem with Wannier states is that they depend on the choice of gauge that I used for U. Okay, so they're not really uniquely defined. Okay, but provided I choose a gauge which is smooth, then they will be localized. And it makes sense then to evaluate a dipole moment in this state. Okay, and so so the point I want to emphasize is that these are gauge dependent but localized. Okay, and so yes.
Are you putting mod phi or something?
Am I putting?
Is that plot for mod phi of phi? Because isn't phi of phi complex?
Mod. This is a. Oh. Yeah. Yeah.
So that would be independent.
No. What? No. Even I mean, the whole thing depends on the gauge, even the modulus of it. Okay. So yeah, if I do a gauge transformation, then this could look complete. Yes. Okay. Right. When I mean gauge, I'm referring to the gauge transformation on U of k. So then so if I do a gauge transformation, then I'm Fourier transforming a different function. I could do a gauge transformation which is nice and smooth. Okay, and so then it'll be localized. Now I guess maybe I should say that this is the modulus. Okay, but it won't be the same. In fact, it may even be located somewhere else. Okay, so but given this choice of a gauge, I can evaluate my polarization now as just, what is the sort of center of mass of my wave function relative to its home base. Okay, and I think one's guaranteed that this will be the same no matter which R you use. Okay, and so if you then take this and plug this definition into here, then I can write my polarization in terms of the block states. And if you plug it in, it takes a little bit of a line or two of algebra, but basically what this gives you is it gives you this. Okay, dk. Yes.
Is it equivalent by saying that R in momentum space is basically minus I gradient?
Yeah, except this isn't well defined and this isn't well defined either. So that's that. You could give that to argument to somebody who you're sure isn't going to ask you further questions.
What's in your mind?
Yeah, exactly. But so let me pose you a question here. So I told you that this is this I explained to you is only defined up to an integer, whereas it looks like this is completely well defined. So where did the ambiguity go? Exactly. So here's the thing. If I do a large gauge transformation on U, then that is equivalent to changing, I have this localized state which I've said was associated with this lattice site. I could do a large gauge transformation and say that this same localized state isn't associated with this lattice site, it's associated with this lattice site. Okay? And so it's the ambiguity of the Wannier states that's where the ambiguity of the polarization sits. Okay. Okay. Any questions? Okay, I have 15 minutes. So what I want to do next is I want to introduce sort of the simplest model system in which one can see this at work. Okay, and this will be where the two-level system with the fits into this story. Okay, so so this model system is called the Su-Schrieffer-Heger model.
So this you can really take. The other one was a kind of a hand-wavy correspondence. They have similar properties. This This is what you meant by a derivation.
Yeah, this is a derivation. I mean, one has to,
You kind of do the intuitive thing. You say,
yeah. Look, and one has to be, for the derivation, it depends what you mean by derive. One has to worry about how localized these are and how, so one could worry about things with this derivation, even though I think in essence it's correct. Okay. So I'll just say this actually is not the original derivation of this. There's another derivation. When I get to the probably tomorrow, I'll talk about the Thales pump. And so Thales did basically used a different derivation, which was basically what he did was to again imagine that I'm changing. Let's see, do I have that still? Oh, I erased it. So so when I talk about the change in the polarization by tuning some parameter, what you can do is you can say, as I'm tuning the parameter, then the polarization is changing, so there's actually a current flowing. Okay? And so you can compute that current using linear response theory. Okay? And using basically the Kubo formula. And if you integrate that current, then that's another sort of more rigorous derivation of this kind of thing. Okay. So that takes some algebra too. So I'm not gonna do that algebra for you, but yeah.
Is there a similar thing true for polarization in 2D and 3D, that it's only defined up to, that it behaves like a very phase?
Yeah. Well, there, of course, the polarization defines the, in 2 dimensions, it defines the charge per unit length along the edge. So that's the edge charge, and there it's the charge. So that's ambiguous up to having, adding an electron per unit cell along the edge. Okay, and so that's the ambiguity there. Yeah. So it's like adding a filled one-dimensional band at the edge, which would give me 1 electron per unit cell. Okay. So let me introduce the Su-Schrieffer-Heger model. I'm not sure I'm going to finish it this afternoon, but okay. So this is a model that was introduced in the 1980s as a model for a conducting polymer called polyacetylene. Okay, and polyacetylene is basically, it's a chain of carbon atoms with some hydrogen atoms attached to it, so that there's basically it forms a one-dimensional half-filled chain. Okay, and but in addition to being a model for polyacetylene, it actually is a very nice model system to understand this topological phenomena. So basically what it is it's a one-dimensional tight binding model. I'm just going to write it down for spinless electrons, even though in real polyacetylene, of course, you'd have up and down spins. Okay, so let's see where I do this. Okay. Okay, so in doing this, I've made a couple of choices. I've defined a unit cell that has an A sublattice and a B sublattice. So this is my unit cell, okay, and my lattice constant, call that A, okay, and then I have T1 and T2 hopping between there. Okay, and so so for T1 equals to T2, then it's just a half-filled band. So it's a 1D metal. And so if I just do the simple band structure, so when T1 is equal to T2, then you really just have, every side is the same as every other. And so I can imagine drawing an energy band that looks like this. I could draw a smaller unit cell with whose size is a over 2. So this goes from 2 pi over a minus 2 pi over a. But what it's useful to do is to define this larger unit cell, which allows me to have T1 not equal to T2. And then I have to fold back, and it looks like that. Okay, and so now this is my Brillouin zone. Like that. Okay, but of course if T1 is equal to T2, then there's no gap here. Okay, and it's kind of like the empty lattice approximation for the nearly free electron gas. Okay, so I haven't turned on any periodic potential yet, but when I make T1 not equal to T2, then I open a gap. In particular, I could have T1 bigger than T2, in which case these bonds are strong and these bonds are weak. Or I could have T1 less than T2. In which case it's the other way around. In either case, what will happen is we open up a gap. Like that. Okay, and so the point that I want to make is that there is a sense, and we have to be careful about what sense this is. There's a sense in which these two are topologically distinct insulating phases. Okay, and so what I want to work towards is figuring out what the polarization is in this case, in these two cases. Okay, and I think I can do that in the last few minutes. So let me do that, and then I'll finish. So in order to figure out the polarization, we need to figure out what the block Hamiltonian is. And so it's not too hard. Actually, I can do it here. It's not too hard to Fourier transform this, and so then you get Hamiltonian, which is going to be a sum on K, CK A dagger CK B, and then there's going to be two terms. There's going to be the T1 term and the T2 term. The T1 term, I stay in the same unit cell. And so that doesn't get any factor associated with it. The T2 term, I jump from the I unit cell to the I plus 1, and so that's going to get a factor of T2 e to the I k a. Okay, and then plus Hermitian conjugate. Okay, and so so I can write this as sum on K of some 2x2 matrix HAB of K times CK A dagger CKB, okay, where little a and b run over capital A and B. And so then what this matrix is going to be is it's simply going to be, well, I can write it as D of K dot sigma. And so this is like the sigma plus piece, and the Hermitian conjugate is going to be like the sigma minus piece. So the sigma x piece is going to be the real part of this, which is T1 plus T2. So dx is equal to T1 plus T2 cosine Ka, and dy is, I think, going to be minus the imaginary part of this. So it's going to be minus T2 sine Ka. And then, of course, dz of K is equal to 0. Okay? And so so now we can sort of, so if I want to compute the Berry phase, I want to compute the polarization, what I need to understand is the Berry phase associated with the ground state of this Hamiltonian when I go around the Brillouin zone. Okay? And so what the ground state is going to be is it's going to be a spin pointing in the d direction. And so so let's think about what that looks like. So so let's suppose that T1 is bigger than T2, and so so the d vector sweeps out a curve in the dx dy plane, and when T1 is bigger than T2, then you can see that dx is always going to be positive, right? This term is always going to beat this term, so it's going to look like this. Okay, and so if I think of a spin, it's going through a thing that goes like this. It doesn't sweep out any area. So the Berry phase is 0. It's 0, and so P is equal to 0, mod E. Okay? On the other hand, if T1 is less than T2, then when Ka is equal to pi, then dx is going to be negative. Okay, and so it's going to look like this. Okay, so it's going to go around the origin. And so now if I imagine following the unit vector, it's going around by 2 pi, so it picks up my favorite minus sign. So the Berry phase is pi, which says that the polarization is E over 2. Okay, so so this actually makes a lot of sense if you think in terms of in terms of these cartoon pictures here. Okay, so imagine, so let's take the extreme limit where the smaller of T1 and T2 is actually equal to 0. Okay, so then basically you have an electron which is localized on this bond, an electron that's localized on this bond, an electron that's localized on this bond. Okay, and if I then switch to the other state where T1 is equal to 0, then what I've done is I've taken that electron and I've moved it over by 1/2 of a unit cell. Okay, and if I move the charge E by 1/2 unit cell, that changes the polarization by E over 2. Okay, and so it's actually easy to understand why these two states differ in their polarization. Okay, and so this is something that you can see by understanding the Berry phase. Okay, so let me just close with a couple of comments about this.
Wait, can you say again why it matters if it's curve zero?
Because if here,
Yeah, that's the only place.
right, because then the Berry phase. So if I think of what the solid angle that is swept out by d of k as I go around this, since it goes around the origin, it's going around like this. Okay, so it's sweeping out a solid angle which is half of the sphere, which is 2 pi, which then gives us a Berry phase of 1/2 that, which is pi. Okay, whereas in this case, instead of going around, it's just going like this. Okay, so it's not. Yes, exactly. So both of these you have to. So so of course it's living on the equator of the sphere. In this case, if I have a unit sphere that looks like this, it's going around. Whereas in this case, if I have the unit sphere, it's going up, then it's coming back, and then it's yeah. Okay. Let me just say so one question. Okay, yeah, question.
Yeah, I just get confused about the last argument you made about moving over.
Yes.
A lattice like that, but I could have drawn the other set of points anyway. So.
Well, but then I'm not sure what you mean by polarization in that case, right? So there is some locality built into that notion, right? So I think certainly you can imagine going from this picture to this picture by picking up an electron here and moving it over. If you're insisting on having the B sublattice live somewhere else, then you have to refine what you mean by this polarization. Okay. So, but that leads me to a thing, which is that there's something kind of funny about this. Okay, and maybe some of you can recognize where the problem is. Look. So these two phases, they look the same. Right? Now, I didn't need to draw them going up and down like this. I mean, I could have drawn them just on the line. In which case, this phase and this phase, they look the same. So how could it be that one of them has a Berry phase of 0 and the other one has a Berry phase of pi? Which one is which? Why could that be? What?
Just the difference, man. Difference in that polarization.
Well, that's certainly true, but who decided which one was pi and which one was 0? Well, so the p is defined mod e. So this one is definitely 0 mod e, and this one is definitely e over 2 mod e. Good. Exactly. You got it. So remember, I made an arbitrary choice, which is I defined this to be my unit cell. Which means that if this is the strong bond, that's what I'm calling polarization 0. Okay? And this one then is the other one. So that's exactly the place where I decided that this one is this one and this one is the other one. Okay. Good. Okay. So now, of course, you might say that, well, that's kind of a unsatisfying thing that I had to make this choice. Why couldn't I do it in a way where I didn't break the translational symmetry in my choice of what the unit cell is? Okay. I could have chosen a gauge in which I put I put, e to the minus ika over 2 on this one and e to the plus ika over 2 on this one. And that doesn't break the symmetry of the sublattices. But what that does is that creates another problem, which is that this block Hamiltonian then is not periodic mod 2 pi. Okay, and so we're stuck with one or the other. Okay, and I chose to have a Hamiltonian which is periodic going around the Brillouin zone. Okay, in general, the Hamiltonian only has to be periodic going around the Brillouin zone up to some gauge transformation. Okay, but I chose it to be completely periodic. Okay, and then one more comment, then I'll let you go, which is that the sense we need to, and I'm going to pick up on this tomorrow, which is to think about the sense in which these two are topologically distinct. Okay, so in other words, what's the sense in which this Berry phase of 0 and pi are really sharply quantized? So notice something essential had to happen here, which is that dz had to be equal to 0. Right? Because if once the d vector can tilt out of the plane, then there's no reason that the Berry phase has to be either 0 or pi. Okay, and so you could ask the question, well, why is that here? Okay, why am I not allowed to add a perturbation in which I get a dz? Okay, and so the answer to that is symmetry. Okay, and so we need to actually go and think about symmetry in the Su-Schrieffer-Heger model. If we don't impose any symmetry, then you can have a dz, and there's no topological states in one dimension. Okay, and so we need to, we can't be too quick to say that we have these two one-dimensional topological phases. Okay, so there's another ingredient of symmetry that needs to be included in that discussion. Okay, so I'll pick up with this on tomorrow. Any other questions? Yes?
Is there a chemist's interpretation of those double lines and single lines?
You mean double bonds and single bonds? Yeah, that's what it is.
I don't know much about chemistry.
Well, this is the picture that the chemists draw. Yeah. I think it's Yeah.
I missed what you said about, so if I choose a unit cell, let's say, to be shifted by...
If I chose this to be my unit cell.
Right, so what would happen, let's say, you're saying T1 greater than T2, why would then not give you pi? E over 2?
Well, so then what I would have had is I would have had T2 plus T1 e to the I ka.
And then you work...
Everything would have been switched. Yeah. Okay, I think we're finished.
So we're going to stick around, we're going to have introductions. We're going to go around the room and have each one of you say a couple of words, whatever you like, whatever you think is important about you. It can be all the way from science to what kind of alcohol you like to drink, or what do you like to do outside of physics.